welcome to the NPTEL Power System Protection course. So, we are in the relay lab, we will have the experiment number 2 on directional overcurrent relay. As usual, we will first go to the basics, what will be covered in this laboratory, and then we will have the circuit diagram, the corresponding connection. We will show the different connections in the table, how we are proceeding for the testing of this relay, and then we will have the different settings of the relay. We will show that also in the relay how we are setting through the PC, and then we will go for the recording, the create fault and have the recording of this relay and show it that how the corresponding relay performs. So, let us go to the basics, what we like to cover here. So, this is on directional overcurrent relay characteristic verification. So, few things which we will cover here is on the circuit diagram, the corresponding theory on which this overcurrent directional relaying operates, and then the relay settings and the observations and verifications. So, in the module for directional relay, we have already studied that how the corresponding directional relay functions and what is its role played in the protection of different elements in the system and so. Just to refresh on that basics, we see that the corresponding direction information is the direction of the fault with respect to the relay position. So, if we consider these line sections, we have a relay at bus M and a fault at F, which is the forward direction fault from the M bus relay. So, for the protection of this, if you see this corresponding voltage at bus M, so if the corresponding phase A voltage happens to be V A and the fault happens to be in phase A to ground, so then the corresponding current lags the corresponding voltage by certain angle, and the angle is the angle impedance angle of the line. And when the fault happens to be behind the relay in the reverse direction, so that is this F 2 fault here, with respect to this bus voltage V A, this is again a phase A to ground fault, then the corresponding current leads the corresponding voltage by the corresponding angle. So, what we already discussed is that this current will be the for this F 2 fault, the current will be fed by this N source, and for F 1 fault the corresponding current will be fed by this L source. So, therefore, we clearly see that there is a reversal of current which will be observed by this corresponding relay at bus M. So, this reversal of current, so this means that if this is the forward looking current, then you can say that the reverse current you can say that will be the reversing of this current. So, that leads to the situation of discrimination, the angle between the corresponding voltage and current is indicative of the direction of fault. So, for that perspective, as usual many times in the distribution system and other systems, we the corresponding overcurrent relay plus the directional relay are being used. So, we call these corresponding things to be overcurrent directional relaying. In that aspects, both overcurrent and the corresponding direction are to be satisfied for the trip decision. Otherwise, if anyone does not satisfy, the relay will not operate for the trip decision. If the corresponding current happens to be less than the corresponding setting current, the overcurrent will not function, the overall the relay will not have a trip decision, and if the corresponding direction information where the corresponding between the voltage and current does not happen to be the within the corresponding settings, then the directional will not operate. So, any one of these does not operate means the overall you can say that the relay will not go for operation perspective and so. We know also that there are different principles to for the characteristic to obtain the required characteristics of the relay, that is whether the fault is forward or the reverse. In that perspective, we have positive sequence, phase based, negative sequence, zero sequence based and all these things perspective which we have already learned in our theory, you can say that in this perspective and so. So, what the in this relay the Schneider make relay the overcurrent directional relaying which we are using here is the corresponding current is considered the reference and the corresponding voltage subtends an angle of phi. This phi can be different depending upon the fault position, forward, reverse or so and so, and in the depending upon the network also. So, therefore, this phi can be varied from, you can say that in a range with respect to I. Now, let us for this a specific case we say that the corresponding forward fault on which the corresponding current leads, lags and so falls in a range, and the range is defined as shown here, that the with corresponding current as the reference, gamma below this reference one in the negative side, the corresponding gamma is the negative angle, and then you can say that in this side the beta angle you can say that is the leading angle. So, this is with respect to this current. So, whatever the corresponding voltage subtends the angle with respect to this current reference, that angle phi, if it varies between this beta in the leading side positive side and gamma in the negative side, within this you can say that this region the directional relay is supposed to work and the in case of angle falls in this range, then the corresponding directional relay will be in the block mode, or it will see as a reverse, you can say the directional fault, and it will not go for operation. So, that is the basics of the operational perspective of the corresponding relay directional part and all this part. When you see the when you go for the overcurrent relaying principle, same as what we have discussed in the first experiment on the that if the corresponding overcurrent in that circuit in case goes beyond the corresponding setting, the overcurrent will operate, and that can be of instantaneous, that can be of moderately inverse and variety of things like we have discussed for this overcurrent relay. Now, for this verification, so we have the corresponding circuit diagram here. So, our directional overcurrent relay is MICOM P138 by the Schneider Electric, and that has its own input, you can say that perspective, and we have two important things here. One is the corresponding current input to the relay, which goes for this overcurrent principle. In case of overcurrent, the relay will go for this one position or the trip position decision making process it participates. If it does not happen through that, then there is no question of trip. Now, on the direction information, the angle between voltage and current that happens to be there. So, therefore, we have a 3 phase input voltage to this particular 3 phase relay, and this voltage angle the voltage angle is being modified by this phase shifter. We have a phase shifting arrangement here to modify the angle, because we essentially require the angle between voltage and currents to be changing. So, already mentioned that we take the corresponding current to be reference, and with respect to that current we go on changing the angle of the voltage by this phase shifter arrangement, and then the corresponding voltage is being stepped down to required level and so, and then that goes to consider that as an input to the particular relay as a voltage signal. In this case, we are showing only one voltage corresponding phase A voltage input to the particular relay, and the corresponding current to the phase A current to that one, and we increase the current to the corresponding setting value, and in case of the voltage I go on changing the corresponding phase shifting phase of the corresponding voltage by the phase shifter, and then when the corresponding angle happens to be there within the setting in the forward direction, the relay goes for a trip decision, and when it trips this, the corresponding current path is being interrupted, and as earlier mentioned in the overcurrent relay. So, this is the trip, you can say that circuit, the corresponding circuit breaker opens and intervenes the particular network where the current is being high. So, with this we will next go for the different components in the table which we have arranged to demonstrate the corresponding relay performance here. So, on the table we will see the different elements which are being connected for this circuit to demonstrate the performance of the overcurrent directional relaying. We have the supply 400 volt 50 hertz 3 phase supply. This is the phase shifter and works on the principle of induction, and through which vary the corresponding phase angle of the output with respect to this input voltage, and also the corresponding magnitude of the voltage also changes. Now, out of the supply system we take in one phase the phase A particularly for this arrangement, where we are injecting the current to create a fault. So, that the corresponding current exceeds then the relay goes for the trip decision on the overcurrent principle. Now, for the directional part with respect to this current and voltage, we change the corresponding angle by the phase shifter that of the voltage. So, these signals of this voltage and currents are being input to the relay. So, this is our MICOM P138 standards make relay. So, this relay is multifunctional, and in this case however, we are using only for the directional overcurrent principle perspective, and so this can be used for any other perspective like differential and simpler overcurrent and so. Now, on this one, when the relay makes a trip decision, that sends the command to the particular breaker, and the breaker opens and trips the corresponding network where the corresponding current is being high and where the corresponding the direction of fault is in the forward direction and so. So, that the corresponding characteristic of this overcurrent directional relaying will be verified by injecting different currents, and when the current exceeds the corresponding setting and the corresponding angle between voltage and current happens to be in terms of this setting in the forward direction, the relay trips, otherwise relay plugs. So, that we like to verify. But on the top of that, to have the corresponding angle, whether we are getting the correct angle between the voltage and current. So, in the oscilloscopes we are finding out the checking, we are able to see that the corresponding voltage signal and current signal, and from there you can say that adjust the corresponding angle, that what is the corresponding current situations, and then is it that in the what is being provided by the relay is in accordance with the circuit condition or not, that can be we can see very correctly from the oscilloscope with the corresponding voltage and current. Then through the, as already mentioned, this is a numerical platform. So, in the PC we will have the different settings and we will observe the different trip command, the corresponding value of current, voltages, and the particularly our interest is here the angle perspective. And then through this the clamping meter we can see the how much current we are injecting to the relay at a given instant of time in that particular phase, through which we are trying to create the fault level of current. So, with this we say that now we will go for the different settings which will be there in that relay, and then we will demonstrate that how the corresponding relay is performing for the particular setting. So, for this experiment first case we will have a setting, and the setting will first fix in the for the relay through this PC, and then we will see how the corresponding relay performs for that particular setting. So, that is what our target is to verify that whether the corresponding relay is performing properly as per the setting or not. For that we have two settings as already mentioned, this is directional overcurrent relay. So, we have overcurrent setting and we have directional. So, in the overcurrent perspective like the we have taken in the overcurrent relay experiment, same we have considered here the IDMT inverse definite minimum time characteristics, IEEE the moderately inverse curve we have picked up, and the corresponding expression for that is same as what we have considered in the earlier discussions. This is also well addressed in our theory also. So, the corresponding k, alpha and L values as per the IEEE provided in the IEEE standard. So, then this gaps happens to be this. So, we expect that it will follow in terms of the overcurrent relay that perspective, that is one aspect, but here our objective is to emphasize more on the directional relay perspective. So, with this setting consider for this the corresponding settings consider for this relay two things. One is that corresponding overcurrent. So, 5 ampere is the nominal current here for this overcurrent, and the pickup setting is 0.3 times I nominal. This can be our options, but we have taken smaller one, so that the injection of current requirement will be smaller. So, that you can say it is the options, and the corresponding pickup current becomes 1.5 amperes. So, the overcurrent will go for the decision in case the corresponding current exceeds 1 ampere 1.5 ampere, and the corresponding time will be governed by the IDMT characteristics as with the IEEE moderately inverse curve. The second setting is on the directional part, and on the directional part, as already mentioned about with respect to the current as the reference, this below consider that negative part negative one below the corresponding reference current I, the angle is gamma, and above that you can say that the leading part is beta. So, therefore, the corresponding beta angle happens to be 135 degree and gamma angle happens to be minus 45 degree as per the particular case which we like to consider verify. So, what does it mean here that when the corresponding current exceeds 1.5 ampere, and in addition to that the corresponding angle between the voltage and current falls within this range, the relay will trip, otherwise relay will remain silent or block. So, that is what we like to see. We like to verify that whether the corresponding current is more than this one, if so whether the angle happens to be within this you can say that limit of gamma and the beta in this range, and if that falls in the range whether the relay is tripping, and when it falls in this range whether it is blocking or not. That is our purpose of verification through this. Now, we will go you can say that to how the corresponding settings are being fixed in the relay. Now, we will see how the corresponding settings are being done in for the relay through this PC, and then we will demonstrate how the corresponding experiments can be carried out for the verification of the directional overcurrent relay. For that if you see here that the settings for the particular MICOM relay, we have the characteristics as already mentioned that we are considering IDMT characteristics IEEE moderately inverse, and our setting here is 0.3 of the I nominal, where I nominal is 5 ampere we have considered, and the corresponding angle, the beta angle is 135 degree already mentioned, and the gamma angle is minus 45 degree for this case. So, the first setting we have set like this for the both current and for this voltage part. Now, what we will see that these settings are for the particular relay operation, and then we will go to the system side. In the system at this point, if you go to this we will have the corresponding with these settings we will have this corresponding relay operation, and we will see what is happening through the particular arrangement in this case. Now, we are going to the pulling the corresponding data that is coming from the relay, and if you see here the corresponding I nominal is 5 ampere, that is coming from the relay as per the setting. The angle between the voltage and current here happens to be minus 89 degree, which I like to check, and the fault current is 0.242 I nominal, 0.3 times of this what we are getting, and the current in the primary side is 1 ampere. So, this current which is being set now is in terms of this 1 ampere current. If you see from this our clamping meter, it is clearly showing in this 1 ampere 1 ampere here. Now, so therefore, because this corresponding current is the below the corresponding 1.5 ampere as per the fault current level. So, therefore, you can say that it is not operating at this moment on the overcurrent principle perspective. In addition to that, because our gamma is set to minus 45 degree, so it is beyond that angle also. So, neither the directional relay is also in the operating mode of the particular case. Now, to verify the angle, because our importance is on the angle perspective. So, to verify the angle, if you see the corresponding oscilloscopes, so you see here the corresponding two curves are there, the blue curve is current and the corresponding yellow curve is the voltage. So, you see here the corresponding to this perspective, if you see number of the divisions for cycle. So, here if you say one cycle of this blue curve, the 1, 2, 3, 4, that 4 gives us the 360 degree. So, each block gives us 45 degree. So, the corresponding things if you see here clear, it is very close to the 90 degree case. So, this shows that the corresponding angle which we are obtaining here in our in this case is the angle between voltage and current happens to be as shown here is 89 degree. So, that means that our angle is in agreement with the what is being the corresponding voltage and current angle, which is given to the input to the particular oscilloscopes and to the relay, both voltage and current of phase A. So, that reveals that our current and the voltage, the angle which is which are the essential part of the decision process are in agreement with the circuit in the relay perspective and so. So, then what we will do that to have this trip operations, we will go for this current increment first. If the current exceeds, then relay is to expected to be trip if the corresponding angle happens to be the within the limit that beta and gamma, within that beta and gamma limit perspective. So, first we will go for this increment of current and we will see that the corresponding current increases the beyond the pickup setting, and then you can say that we will say that that the overcurrent principle should there. So, now the corresponding current happens to be there here, you can say that more than 1.8 1.7 ampere 1.8 ampere, and as per here this is 1.8 ampere. So, it is above the corresponding the things. We can set more also. Here it is clearly showing this the 2 ampere range. So, this is 2 ampere. So, here also you see here 2 ampere of current. So, that is greater than our pickup setting. So, the overcurrent relay goes for the decision of the trip mode. Now, however, because the direction here is minus 89 degree. So, therefore, the corresponding directional relay does not permit, and the relay is not, you can say that, going for trip decision. Now, to comply that, you can say that both directional relay and the overcurrent perspective satisfy the trip mode. So, therefore, we will change the corresponding angle through the phase shifting transformer, and then we will see that the corresponding angle comes within the range, and we will slowly vary the corresponding angle and see that whenever it happens to be there within the range, then the relay is expected to trip. So, for that we go on changing current remaining same 2 ampere which is in the trip region, and we go on changing the corresponding angle. So, if you see here the angle is going to reducing. So, if you see here on this perspective also the angle goes on changing here in this oscilloscope, and we will see, you can say that on the when the corresponding angle reaches to when the angle reaches what the corresponding happens to be there. So, slowly go on changing the angle slow. So, it is already gone for minus 70, still not is not tripping. It has already reached to minus 65, it is still not tripping. So, it means that this is in the reverse mode region. When it reaches to minus 45 degree, as in the set, you can say that it should go for the trip. It is minus 60, still not tripping, current is still 2 ampere. So, it is in the operating zone. So, we will say now it is minus 54 degree, here also it is not tripping. Now, it is minus 51 degree, it is also not tripping, minus 50 it is not tripping, minus 48 it is not tripping. Now, let us slowly reduce this further, yes. Now, this is minus 45 degree, and you see here the corresponding things here, and then we will check, you can say that in terms of that. Now, we see here the corresponding current is 2 ampere exceeding the limit, and then the corresponding angle has already reached to minus 43 degree. So, it is both the directional and the overcurrent relay both satisfy the condition. So, the relay is expected to trip in this case for this perspective. So, we see that the relay the decision time of the relay depends upon this IDMT characteristics, and the relay is expected to trip for this particular case. So, now you see that like this experiments will be carried out for the range for this range. So, we will go to another setting in the positive angle perspective towards the beta angle, and see that whether the corresponding relay is tripping or not in the next situation. Now, in this case again 2 ampere and the angle is 133 degree, and the relay tripped here successfully. So, you see that our setting beta side is 135 degree. So, the relay is expected to trip satisfying both the direction and the corresponding overcurrent principle. Next, we will see that whether beyond this 135 degree setting the relay will operate or not, as expected it should not operate. Let us see another case. See here the current is still 2 ampere. So, it is in the overcurrent mode, and then the corresponding angle, the load angle happens to be 140 degree. So, that is beyond the corresponding beta limit of 135 degree, and the relay is not operating even if we have waited for a long duration of time as expected. So, it means that if you see the corresponding angle also, clearly it is showing a large angle, and this in this range the corresponding relay is not operating. So, we verify that at different points that the relay is following what is being expected for forward fault in the region of gamma to beta, and with current exceeding the corresponding setting of peak of setting of 1.5 ampere, the relay is operating, and in the reverse fault case beyond the corresponding angle and that set angle it is not operating. So, like this for this relay we took several observations throughout, and for different situations and different settings, and we find that the corresponding directional overcurrent relay is performing correctly. For the case 1, we have the nominal current of 5 ampere, pickup current setting is 0.3 times of the nominal is 1.5 ampere setting, and the characteristic curve taken is IEEE M inverse, which governs the corresponding operating time, and then the corresponding beta angle is 135 degree and gamma happens to be minus 45 degree as already clearly mentioned. In this case we took several observations and some of them are noted here. So, the load angle varies here 1 degree, 15 degree, 27, 42 like this, and also this in the negative region also, and whether the relay tripped or not is also shown. You can say that for each of the corresponding angle as we have described during the experimentation. So, for 1 degree it tripped, for 15 degree also it tripped, and like this these are the trip, you can say the region for this. So, till 135 degree it tripped, and beyond 134 degree the corresponding for 138 degree, 148 degree we find here you can say that all the node trips and so, and when it happens to be again minus 6 degree, minus 18 degree it trip, and minus 39 degree also trip, minus 44 degree also trip, and minus 46 degree not trip, because our gamma setting is minus 45 degree. So, therefore, there is a clear demarcation between trip and no trip with this gamma value, and other you can say regions it did not trip for the higher angle in the negative side. In the positive side if you see the angle, then the trip and the no trip, the boundary is you can say that between 134 and 138 our beta angle happens to be 135 degree. So, therefore, if you plot these two considered things from the observations to and what is the corresponding expected things. So, trip revision is observed to be within minus 43 degree to 134 degree in terms of this is the red one is the observed one, and the set one is the solid line with the blue lines that is 45 degree to 135 degree. So, we see that the characteristics, directional leading characteristics in the forward region as per this setting follows pretty accurately, and in case of that, and therefore, we can say that the directional overcurrent characteristic is correctly verified. Another case for our checking to observe this one. So, again we set the corresponding current to be same and same IDMT curve, but the beta is changed to now 170 degree and gamma is changed to minus 10 degree now, and we took all the observations throughout like that, and we see here you can say that in this table in the positive region. So, the boundary where you can say that the trip is 165 and no trip is 174. So, in between the happens to be this beta 170, and in the negative one the trip and no trip happens to be between minus 6 and minus 13. So, we say the gamma is minus 10. So, this means that if we plot these two now, the solid line is for the set 1 and the dotted line is the observations taken from this one. So, therefore, you see that both the corresponding observations line is very close to the solid line, and then we say that the relay is following the corresponding settings in accordance what is being set through the set for the relay. So, thus in overall we can conclude that the directional overcurrent link principle which is being followed here is in agreement with the requirement, and the peak 138 MICOM relay is functioning properly as expected for this case. Thank you.